looking forward to this webinar on 800G, the race to 800G. As we know, 400G ZR is just starting to come to market now. So what we're talking about here is sort of the next thing on the horizon. We've got two great companies represented here. First, Inphi, which, as many of you may know, has been in the news a lot over the past year for both business reasons, which we can't really talk about in this webinar, as well as for the technology reasons. It was about a year ago that they started sampling their Spica 800G 7 nanometer DSP, which provides a pathway to things such as 8x100G optical transceiver modules. Very interesting. And of course, we have the perspective of one of the largest hyperscale cloud operators in the world, which I think will give us really a reality check as to whether this next wave on the horizon is something that is coming soon, perhaps, or perhaps a little bit later. So we've got a lot to talk about. Let's kick it off. Radha, take it away.
Hi, this is Radha Nagarajanwe from Inphi. Thank you all for the great introduction. Together with Ilya lyubomirsky, we're going to give you a perspective on 800G. So there are wide spectrum of you in the audience. I'm going to take a step back and just look at data centers, data center architectures, how they've evolved, and where does 800 gig fit in. There's been a considerable evolution, data center interconnects, and data centers in general have gone from sort of hierarchical structures with a lot of oversubscription to flatter and flatter architectures. It's a little bit of an exaggeration. This slide is borrowed from Microsoft. What has happened over the last couple of years? The elimination of layers, very high-speed interconnects between layers, minimization of oversubscription, and data center aggregation. And what has actually driven this is lots of interconnect resulted in driven this as interconnect-rich environment, machine-to-machine traffic, a lot of what we call east-west traffic, and also a very high radix interconnection between servers and sort of elimination of the switching layers for applications that require lower and lower latency. So what I'm going to focus on is radix. And I'm going to tell you why it matters, and then how it drives data center interconnect and interconnect speeds. Here's a chart that we borrowed from Facebook. What it shows is the switch radix versus the number of levels that you actually need to interconnect X number of servers. For example, if your radix is at 32, which is out here, and if you wanted to interconnect 100,000 servers, which is a typical size of a fairly large data center, you probably need 4 levels of network. And if you were to actually go to something like an 128, you need something between 2 and 3 levels. Essentially, you need 3 levels. So by going from one radix to another, radix is essentially in how many small tributaries that your switch gets split up, that determines what your interconnect speeds are. So why do we actually care about radix, at least in this perspective? It sort of drives the interconnect speeds. I have switch generation here. 12.8 is in deployment, 25.6 coming up, and 51T is the one after that. At 12.8 at radix 32, sort of a simplified view though, even for a given radix, the data center architectures are quite a bit different between different operators. You have a 400 gig interconnect, or if you had in 128, the examples of both, your interconnect speeds, optical interconnect speeds become 100 gig. And as you go to 51T, at 25.6, you go to 800 and 1.6. At radix of 128, you go from 1, 2, and 4. As you can well imagine, we have the whole breadth of interconnects out there. and deployed differently under different architectures, all the way from 1 to 400, and 800 is coming. Trust me, I can say who is deploying and who isn't. That isn't the focus of the talk, but we are getting there. So we want to go 2x in speed scaling. What do? Let's start with 400 gig. Today, 400 gig, two flavors. One is between data center interconnects, 60 gigabaud, 16 QAM 16, 1 Lambda, or 53 gigabaud PAM4, 4 Lambdas. This is what a PAM signal looks like, and if we take this and put them in 2 axes, this is what a QAM 16 signal looks like. The easiest or the easier way to scale is, why don't you just increase the number of wavelengths, 2x the number of lambdas? And that is the path that 800 gig, 8 lambdas, the first implementation of 800 gig inside data center is following. The issue usually is power size, cost, and it's not really scalable. So what do you do after 8? Even 8 is a bit of a challenge. The next axis is, why don't we just increase the baud rate by 2x? And the challenges there are the analog bandwidth. But it looks like we have a handle on analog bandwidth, because the next axis is even more complicated. For a given bandwidth, can we just increase the modulation format? Complexity, SNR, you don't really want to be dealing with PAM16. That's what it takes from PAM4 to increase double the baud rate, or QAM 256. And then let's look at some engineering trade-offs. Would a QAM 64 90 gigabaud work, or a PAM6 90 gigabaud work? The consensus that's building, an 800 gig single lambda would most likely be 120 gigabaud QAM 16 and about 112 gigabaud PAM4. We'll get into the details in a moment. All right. Technology choices in data center interconnects. A view at 100 gig. Inside data center 802.3 PSM4 CWDM4 and 2 to 10 kilometers LR4, also CWDM wavelengths. 10 to 100 kilometers, there were two options, PAM4, in which Inphi deployed together with Microsoft, and Coherent, between 100 to 600 gig Coherent DWDM, and a variety of Coherent formats going all the way up to 10,000 kilometers. At 400 gig, there was a real opportunity, and has been exploited, to collapse a lot of these into a common format, although I wouldn't claim that you can go up to 10,000 kilometers in commercial deployments, but ZR Plus, they are making an impact. Although at really long distances, there are still custom-made deployments, but ZR and ZR Plus would cover things all the way up to about 1,000 kilometers. And two things happened. One is the collapse of the Coherent formats and into one, and also the DSP type processing moved inside the data center. At 200 gig and 400 gig is essentially PAM4. At 400 gig is 100 gig per lambda, and at 200 gig is 50 gig per lambda, DR4 and FR4. And 800 gig view to the future. We think it's going to be 200 gig per lambda. We'll make a case for it. In terms of power consumption, in terms of complexity, 200 gig per lambda makes a whole lot more sense than 100 gig per lambda in 8 wavelengths. When it gets 200 gig per lambda, you are probably going to be dispersion limited even at 1310. So it might just be limited to 2 kilometers. And you'll probably have Coherent moving closer and closer into the data center. We don't think Coherent is going to move inside the data center anytime soon. And just for to get some discussions going, there is a possibility that we may actually have a CWDM LR Coherent with a distance optimized and a lower power DSP. So 400 gig 4 lambda, 800 gig 8 lambda, 800 gig 4 lambda. The variety of trade-offs here, going from 50 gig PAM to 100 gig PAM. The number of host lanes remain the same. That's sort of important. Going from 100 gig to 200 gig. What do we think this transition would happen? It's got to do with DSP area, DSP power. Although the analog bandwidth requirements are going to go up, from power consumption perspective, I think this transition would happen. That we would go from 100 gig PAM to 200 gig PAM on the line side. And we could potentially accommodate all of these in a QSFP-DD or a OSFP form factor. The question that always comes up, also another point is moving to 800 gig for Lambda. You need 200 gig per Lambda to get to 1.6 T modules, which I showed you in the slide on radix. Why wouldn't you do an 800 gig coherent 1 Lambda inside data center? There are a number of issues here as to why coherent may not move inside or will not move inside data center at 800 gig. Power. The power is still going to be high for 800 gig coherent 1 Lambda. Backward compatibility to PAM4, very important. The established infrastructure right now inside data center is PAM4, and backward compatibility will matter. And synergy with copper applications. There are some challenges for PAM4. I said reach extension beyond 10 kilometers. I would say reach extension beyond 2 kilometers is a challenge, but a variety of other solutions can be brought to bear on this. But we think it's PAM inside data center 800 and 16 QAM outside. All right, for those of you in the audience who do not deal with pluggable modules, here is a primer. The PAM4 100 gig that we deployed for DCI between data centers is what we call a QSFP28 module. And for the 400G ZRs, either a QSFP-DD or OSFP, they're slightly wider for QSFP and slightly longer for QSFP-DD. And for a 1RU, which is typically 1 3/4 inch in height and a 19-inch width rack, both of these formats will accommodate 32 modules, which fits neatly into a 32 radix type data center architecture. So they're slightly different in physical dimensions, but both of these formats will work. So we have been focused on silicon photonics. We have been developing silicon photonics for the 400G ZR and 400G DR4 modules. This is a typical performance of the Mach-Zehnder modulators with over about 40 gigahertz bandwidth and high-speed photodetectors. The first two are prerequisites for 400 gig inside data center. And outside data center, you really have to have polarization maintaining components as well, polarization beam splitters, polarization combiners, low loss, and high extinction ratio. Before I pass on to my colleague, I'd like to show you some of the work that we've done and deployed, something that Jim referred to earlier on. We announced about a year back 400 gig ZR modules, QSFP DD form factor, which is a similar form factor to DR4 and FR4 inside data center, using an advanced 7-nanometer node for the DSP, an advanced silicon photonics node from BiCMOS Foundry. It's 8 by 26 gigabaud PAM4 coming in, 802.3bs format standard. Output is a 1-channel, 1 Lambda 59, 60 gigabaud QAM16, nominally 80 to 120 kilometer span reach. We have a DSP and a silicon photonics engine inside the module. And we've shown this data earlier on. Polarization scramble, 50 kiloradians, less than half dB penalty. And the spec is 26 dB for ZR. And this is a typical 400G switch that you can buy in a market, and a fully loaded spectrum. And you can plug these modules directly into a router or a switch and convert that into a line system. And that is the beauty of pluggable modules, either for 400G ZR or 400G DR4, FR4. And the same trend would sort of follow at 800 gig, where the modules would be switch pluggable. And of course, there's a challenge for cooling, but that would be the same trend that would follow for 800G as well. I am going to pass on to Ilya to look at the details of 200 gig per lambda modulation, equalization, and FEC. Ilya?
Great, thank you, Radha. Great setup and background for the rest of the presentation, where we'll focus on 200 gig per lambda PAM technology, and specifically I'll try to give you a flavor on some of the important trade-offs with modulation formats, equalization techniques, and forward error correction. Yeah, Radha, if we can go to the next slide. Okay, great. So I'd like to start first to give a little bit of background on the existing 400 gig standards, because I think there's some interesting trends there that perhaps could give us some insights on 800 gig. So here I've organized the IEEE and MSA standards according to kind of the generation and the reach. At the top, I have the 400 gig standards based on 8 lanes of 50 gig PAM4. And you can see that these standards pretty much cover all the key data center applications, from the short reach multimode at 100 meter based on parallel multimode fiber, the FR8, 8 lanes of single mode LWDM going out to 2 kilometers, LR8 going out to 10 kilometers, and even ER8 going out to 40 kilometers. The current generation of standards is based on 100 gig per lane, so 4 lanes to give a 400G rate. And as Radha pointed out, one of the important trends is to reduce the number of optical lanes, to reduce the optics cost and the power of the modules. So that's the current generation based on 4 lanes of 100 gig per lane PAM technology. And again, we're able to cover most of the key data center applications, the short reach, multimode, SR4, DR4 at 500 meters, FR4 going out to 2 kilometers, and LR4. One, I think, interesting trend here, though, is that we're starting to see some of the limitations of going to higher baud rate using, intensity modulation and direct detection, and especially the impact of fibrochromatic dispersion is starting to, have an impact on the reach. So, for example, the IEEE decided to limit the LR4 reach from the traditional 10 kilometer to 6 kilometers to mitigate some of the dispersion penalty. And even though we have an MSA that has extended this reach to 10 kilometers, essentially kind of leveraging the industry advancements in DSP technology and equalization that can mitigate this dispersion penalty, still we're starting to see the impact of fiber impairments on scaling the baud rate. And I'll talk a lot more about that in the following slides in the context of 200 gig per lambda. Now, the IEEE recently started a new project beyond 400 gigabit Ethernet. And although this project is just starting off and we're going to start working on the objectives, I can speculate here that most likely we'll have an 800 gig objective, and very likely we will look at PAM technology for 200 gig per lane and going out to 1 to 2 kilometers, FR4 type of distances. And I believe, we'll need a stronger FEC to deal with, going to higher baud rates. And most likely we'll need, we need to leverage the DSP technology to mitigate some of the impairments that we're going to have to deal with when we scale to higher baud rates. So in the next slide, I'd like to actually go over the key impairments in an optical 200 gig per lambda system. So here I show a little cartoon just describing the key components in a PAM4 optical interconnect. The key components are the DAC at the transmitter, the driver, and the laser modulator. We have, of course, the fiber link, and at the receiver, the photodiode, the TIA, and the AFE and ADC. And some of the key impairments that we have to consider are the transmitter analog bandwidth limitations and electrical reflections. So as an example of that, I borrowed a picture from an 800 gig pluggable MSA white paper shown below here, which shows two designs for 200 gig per lambda transmitter based on EML technology. And you can see in the frequency response, the bandwidth, the analog bandwidth is around 50 gigahertz, and there are lots of ripples in the frequency response, perhaps due to reflections in these interconnects and components. So that's something that's very important to consider in our designs, and I'll focus in more on that in the following slides. In the optics, we have to carefully consider the laser rim noise. It's a level-dependent noise, which has a very important impact on higher order modulation, and in particular, it would impact PAM6 more than PAM4. And I'll show you some of the ramifications of this in the following slides. And for the fiber propagation, the fibrochromatic dispersion, as I mentioned, is a key impairment. And we're already seeing that at 100 gig per lane. The fibrochromatic dispersion penalty actually scales quadratically with baud rate. So we expect this to be even more of a limiter for 200 gig per lambda. And I'll have a separate slide where I'll just focus in on the chromatic dispersion impact. There are other optical propagation effects like PMD. And at the receiver, the key component there is the TIA, and we have to carefully consider, the specifications of the TIA noise, nonlinearity, and analog bandwidth. So I'll provide a slide which gives an analysis on the TIA performance as well. Okay, so I talked about the impairments. What are the tools that we have in our toolbox to deal with these impairments? Here I show kind of a simplified receiver DSP architecture and try to highlight some of the key components and tools that we have. So first of all, in the analog part, the AFE, the most important component is the ADC. And this is really the component that enables DSP architecture. And today we have ADC technology that can go out to beyond 100 gigasample per second and analog bandwidths of 50 gigahertz or better. In the DSP domain, we have some very powerful tools, starting with linear equalization based on the FFE. And today we can implement FFEs with 10 to 30 taps or more. And the FFE is extremely useful for both mitigating analog bandwidth imperfections as well as reflections and all kinds of imperfections in the frequency response. We can implement a one-tap DFE, which, as I'll show, is very useful for kind of extending mitigating the bandwidth limitations, and it also helps a little bit with chromatic dispersion. And when we're really stressed with a very bad channel, then the most powerful equalization is based on what's called maximum likelihood sequence detection. And we've implemented kind of a simplified low power MLSD, and I'll show you some results on MLSD as well. And finally, a very important tool is the forward error correction. In the existing standards, KP4 FEC is the kind of the workhorse that we use for both 50 gig and 100 gig per lane PAM technology. And it's really important to enable the reaches and also enable low cost optics. And as we scale to higher baud rates, I believe we're going to need stronger FEC. But at the same time, we have to keep that FEC, low power and low complexity and low latency. One of the advantages of the DSP architecture that I show here is that we have available in the FEC module not only the hard decisions, but also the soft information, the reliability information. And we can exploit that information to design stronger FECs while keeping the complexity fairly low. So what I'd like to do in the following slides is to discuss a little bit on FEC, and then I'll move on to the equalization and modulation trade-offs. Here I show a FEC architecture based on so-called concatenated codes. This is actually the architecture that we standardized in the 400 gig ZR standard. It's a very flexible and powerful architecture because it allows you to start with an existing FEC. So in this case, we can start with the KP4 FEC that already exists in the switch host ASIC, and we can build on it by adding a simpler code inside the DSP of the optical module. And we can also, as I mentioned previously, exploit the soft information in the DSP of the optical module, which is very close to the channel. And by combining these two effects together, we can get substantial improvements in performance and the coding gain, while keeping the effect fairly simple in the optical module to keep that power low and the latency fairly low. So this is the architecture we've been working on. And on the next slide, I'd like to show you some simulation results on performance of these concatenated codes. So these curves show several designs of a KP4 FEC for the outer code and different levels of complexity of the FEC for the inner code. Starting with the purple curve, which is just KP4 FEC by itself. Then the yellow curve, we're adding a fairly, like the simplest FEC you can think of, just a single parity check code inside the optical module DSP. And with soft decision decoding, we already get about a 1.5 dB enhanced coding gain. Then the red curve, we're using a more sophisticated Hamming code, extended Hamming code, and we get an additional 1 dB improvements. And we can keep going using more sophisticated, inner codes like the BCH code, two-error correcting code in the blue curve. And what we find is that as we use more and more sophisticated and complicated inner codes, we kind of have a diminishing return in terms of the trade-off between complexity, power, and coding gain. And that we found a good trade-off is actually this red curve, which is using a Hamming code for the inner code. And interestingly, this is also the design we used for the 400 gig ZR FEC standard. And with this code, we'll have an overall coding gain of about 9.4 dB while keeping the complexity and the latency fairly low. So I'm going to assume in the following slides that we'll have one of these stronger effects available to us. And next, I'd like to focus more on the modulation and equalization trade-offs. So here I show some system simulation results on the bit error rate as a function of the analog component bandwidth. So the analog component bandwidth is a very important kind of parameter we have to consider. Here I'm sweeping the bandwidth of all the components, the driver, the DAC, the modulator, the KA, and the ADC. And as we sweep the analog component bandwidth, here we're simulating the bit error rate for both a PAM4 system at 113 gigabaud and a PAM6 at 90 gigabaud. The horizontal dash curve is the FEC limit for one of the more advanced FECs that I just discussed. And you can see some interesting trends here. So for example, with FFE only, which is blue curve versus black curve, we see that there's a kind of crossover point where when you go beyond 45 gigahertz, PAM4 gives a better performance, while for really lower analog bandwidths, PAM6 gives better performance due to its lower baud rate. With a DFE, when we add the DFE, which is shown in the red curve and the green curve, that crossover point shifts to lower bandwidths. And we see that then, PAM4 performs better even at 40 gigahertz and beyond. And when we add the MLSD equalization, which is shown in the pink dash curve, then really PAM4 shows a very good performance, much more robust to analog component bandwidth limitations and good bit error rate. So based on these results, we feel that PAM4 is a good choice for modulation format for future 200 gig interconnects. And in this slide, it just confirms the analysis that I just showed. And here we're just focusing more on the TIA and looking at the impact of KA noise and KA bandwidth. So sweeping out that parameter space and comparing PAM4 to PAM6. And you can see here, red is bad, it's below the FEC threshold. We want to be in the green and blue region, and this slide shows that PAM4 has a much wider kind of good region of operation, which shows it's more robust and a good choice for modulation. So if you go to the next slide, Radha. Here, I just want to kind of finish the technical discussion, focusing on the chromatic dispersion. As I mentioned, that's the key optical impairment as we go to 200 gig per lambda. So here I'm focusing on PAM4 technology and looking at the impact of equalization on the performance. And I'm plotting the simulated optical power penalty as a function of chromatic dispersion. And what we can see here is that with linear equalization, which is the red curve, we really don't have enough equalization power to deal with a 2 kilometer FR4 spec. We need to go to at least an FFE DFE architecture, which should work. The dispersion penalty would be 1 dB or lower. With MLSD, we really are doing very well. The dispersion penalty is below half a dB, and we could potentially even go to longer distances beyond 2 kilometers. So I'm running out of time, so I'll just go to the conclusion slide. So in conclusion, next generation 800G data center optical interconnect should be designed considering the unique application requirements of data center operators. The choice of modulation format, DSP architecture, and FEC requires careful analysis on the engineering trade-offs of analog component technology and optical channel specs. And our optical system simulations show that PAM4 is a good choice for 200 gig per lambda. It's a feasible technology for 800G FR4 and DR4, synergistic with low latency AI, breakout, and copper. Coherent technology, on the other hand, may be the most useful for longer reach applications, such as 40 kilometers and maybe even 10 kilometers, where coherent dispersion tolerance and lower fiber loss at 1550 nanometers are the key advantages. Radha, do you want to add anything to these?
No, this is great, Ilya. We'll yield the floor to Mark, and then we'll take questions at the end of the session.
Very good. Thank you.
So yeah, thanks for inviting me to speak here today, and Radha and Ilya, thanks for the interesting presentation there. I wanted to kind of come around with all the talk about the race to 800 gig and the next gen solutions being just on the horizon, and just kind of hedge that in with a reality check for, I think, at least where we are at Microsoft, may not be indicative of plans for the other hyperscalers and end users of these devices, but at least gives one counterpoint as to where we see things going in our data center ecosystem. And so, like with anything, whenever we start talking about something more than 6 months out in a public forum, it's probably a good idea to caveat it with a disclaimer like the one shown here. It's meant to be a little more tongue-in-cheek than specific legal language, but just all that to say that at least at Microsoft, plans can change quickly, but at the same time, change is slow to happen. It's a big ship, so take what I say here when I'm projecting forward with a grain of salt. First, I want to start out with the question. Is there demand for 800 gig? I think that's the premise of the webinar, and then Radha and Ilya would have you believe that there is. And the answer is pretty straightforward, at least as far as I can tell. Yes, there is demand. I participate in the OIF, and I'm on the board there. And back the first part of last year, we issued a survey to network operators. We issued it to over 25 network operators or so, and had them answer questions about beyond 400 gig, and particularly in scope there was kind of beyond 400 ZR, like the 400 gig coherent applications, but the answers to the questions shed some light on what would be happening inside the data center as well. One of the relevant questions there I have in the top right is, when are you expecting to need a standard coherent line-side interface with capacity larger than 400 gig per lambda? And if you check out the answers, over 70% of the respondents came back with 2023 or before, and another 25% or so said sometime after 2025. But the big takeaway for there is, yeah, people are expecting something higher than 400 gig, and they're expecting it pretty soon. That's 2 years away. The next question, what router port speed do you plan to deploy after 400 gig? And, the vast majority here, almost 50% said 800 gig. Some others said 1.1T or 1.6T. I think it's pretty unclear what the next MAC rate would look like beyond 800 gig perhaps, but and then some answered other. I'm not really sure what they had in mind. You know, one of the interesting things that came back too in the survey response is what people expect the power of these modules to consume. And as you can see there, the powers that people are saying are about where 400 ZR is today. And you know, as we know from history and early engineering projections from what people are looking at for what would be maybe an 800 ZR application, that's going to be quite a tall order. So to me, this tells me that people are already pretty power constrained. They kind of want to have their cake and eat it too. But you know, we'll just have to see how these things play out. So you know, all of that is backdrop for what I'm about to show you, which is the very Microsoft-centric view, I would say. I think it's helpful first, and I apologize if you've seen this in other forums before. We've been showing the next few slides in a few different forums like OFC and ECOC for the last couple of years, but I always feel like it's helpful to level set with the audience on how we build things today, and that better informs, you know, our use cases and requirements for the future. So looking at what we do at 100 gig and 400 gig, how we build our data centers today. So my slides will advance. There we go. So, you know, we start with the notion of a rack, which is comprised of a bunch of servers, tens of servers. And those servers are connected into the network by a top of rack switch. And the connections are made with DAC cables, the direct attached copper, that are about 2 meters in length. And, you know, in our 100 gig ecosystem, they're running off of 50 gig interfaces from the servers. There's typically some oversubscription of the Tor device, and that's usually a single switch ASIC device that has some oversubscription as it goes to the next tier of switches. And those are connected in a cross fabric across multiple, you know, redundant switches with AOC cables, typically about 30 meters or less in length. The AOCs run at 100 gig and dissipate around 2 to 2.5 watts per end. And tens of these racks are chained together across these tier 1 switching devices, and that makes up what we call a row or a pod set. So this is kind of one of the main building blocks that you'd see in our physical data centers. And other thing here is the tier 1 and the Tor devices are typically both single switch devices, kind of the 1RU pizza box type of switch, commodity switch you might have seen on the market. Going to how we then build our data centers, connect our data centers together. Sorry, I'm jumping ahead of myself. How we connect the pod sets together within the data center, a single data center facility. We have what we call our tier 2 routers that are connected to our tier 1 devices across the different pod sets with parallel single mode fiber. And that fiber is actually a permanent part of the infrastructure. It's amortized over the lifetime of the data center to mitigate the cost, but also because we know we will use these fibers across generations. Those are about a kilometer in length maximum, and the tier 2s are, you note they're a different color here. That's to denote that they're multi-chip modular switches that have fabric cards and line cards for separate line cards for northbound and southbound connected ports. And the optics that connect into those devices on either end are typically PSM4, although in some legacy data centers, we might use CWDM4 to cover a longer distance where we don't have that parallel infrastructure. And my note about these being modular switches is significant because it allows us to mix and match clusters of different generations, a 100 gig cluster or a 40 gig cluster. And we do the impedance matching, the term we like to use, of those different generations using the line cards in those tier 2 devices. And everything you see here is what makes up what we call a data center. Now, the way we connect our data centers together within a metropolitan area is maybe a little unique today, but I think people will see more of this type of approach going forward with 400ZR coming onto the market. But what we have is we have two hubs within a region that we identify as RNGs, regional network gateways. And the data centers are connected, again, in a close fabric across the metropolitan area over DWDM line systems using PAM4 technology, which Radha referred to earlier on in his deck. And this is the distances here that we're talking about are typically latency constrained. We say 100 kilometers on average. It's actually a bit shorter than that, but it's to ensure that the round trip time from any server in any one data center to another data center is bounded by a certain amount on the order of microseconds that makes at the application layer to the user if you had storage served out of one data center and compute out of another for the same application, it should feel seamless, like it's coming out of one mega data center facility. And so that's where this distance comes from. Again, the PAM4 modules are directly plugged into the routers here and dissipate about what a gray optic does that generation, around 4.5 watts. And the capacity that we would have is a single percentage of the total server capacity for a given region. For our largest regions today, this is petabits per seconds of cross-sectional bandwidth going across the metro. So just summarizing what this looks like for the 100 gig ecosystem, at 100 gig, down at the bottom, it's the DACs connecting the servers to TORs, 2 meters. The TORs to tier 1s, that's 100 gig AOCs, 30 meters. Tier 1 to tier 2, 100 gig PSM4s at 1 kilometer. And then 100 gig DWDM PAM4 connecting the data centers to the regional hubs and the regional hubs to each other. We egress the regional hubs going toward the capital I internet and toward our private backbone to connect to other data centers across the world using kind of more traditional long haul types of solutions there. So this is what it looks like at 100 gig. Going to 400 gig, you have to watch closely here. Boom, 400 gig. So if you'll notice, basically nothing changed topologically. The only thing that changed was we scaled up the bandwidth of all of these links that are interconnecting the switching tiers by a factor of 4. And this is noteworthy because of the point that I'll get to on my next slide. The elephant in the room here, and something that hasn't been much of a major consideration up to this point in time, and this point in time meaning the 400 gig ecosystem, is power. The equipment, network equipment power consumption is already problematic for the 400 gig ecosystem. And the charts at the right are highlighting this phenomena. Switches in the 400 gig timeframes are projected to be around 3x the power of the 100 gig switches. The optics are coming in around 3 to 4x 100 gig. And this challenges the total power envelopes available in the data center facilities. And so the plots on the right, the one on the bottom, we generated based on some internal data showing over the generations of the server link bandwidths, or you can think of it really as the MAC rates. The power, the relative power of the networking devices versus the servers is ever encroaching. And once you scale to 800 gig, it's up around 20% of the total data center power being consumed just by moving bits, not by the revenue generating servers. Likewise, the plot above it is Facebook's data on, without calling out the specific generations, but showing the same phenomenon that as you go to quote next generation, the network power is a big slice of that pie. And that's bad news when your service is cloud, right? So as I mentioned, it's using power that could be generating revenue. It's capacity that is lost on the servers, to the servers. And it costs money. Obviously, it's just burning power that could otherwise be done more efficiently, and it's not green. It doesn't support our own sustainability initiatives internally to build things this way. And so, looking at it like that, it makes the trajectory of a transition to anything beyond 400 gig, doing things the same way we are now appear all but impossible, or at least very inefficient. So looking at possible solutions, how do we really start to chip away at this problem? One is photonic innovation. And a big piece of that, we believe at Microsoft, is co-packaged optics. And co-packaged optics, if you're not aware, is just the notion of packaging together the switch silicon or any type of system on chip really with the photonic engines that are primarily based on silicon photonics on a common substrate. And by, this is talked about a lot in the industry, but by moving the optical engines closer to the ASIC itself, you can reduce the trace length and SerDes power and really drive efficiencies in power. And what we're seeing is that compared to kind of state-of-the-art pluggable technologies, when you're looking at link efficiency, the power efficiency at 25 picojoules per bit on average for a pluggable, going on board like a Kobo approach, improves that by moving the optics closer and eliminating retimers. But really, you see some great efficiency gains by co-packaging. Almost 30 to 50% reduction in the power that's dissipated by the optics. And even with an eye towards second-gen co-packaged optics, where some additional optimizations could perhaps be made, really driving that down into the sub 5 picojoule per bit range. So we see that as a big area, but we also have to attack it in other ways. For example, collapsing tiers, as Radha touched on earlier, by using multi-homed NICs on our servers, fanning out horizontally and bypassing TORs, and I'll have a little more detail on that later. Having simplified forwarding requirements on our switching ASICs, less fib, less buffer equals less work and less power. Additional integration, things like integrating the encryption directly on the switching ASICs. And lastly, some types of alternate cooling. I show liquid cooling, specifically immersion cooling there, but we're actually studying several different approaches to that at Microsoft. But the big takeaway is we can't just keep scaling link bandwidths. Like what I showed going from 100 gig to 400 gig, that's the last time we can do it like that and continue building things the same way. Next gen systems are going to require all of the above. Additionally, I wanted to just provide this retrospective here. If you look at the rollout of what I'll call our 40 gig ecosystem, our 100 gig ecosystem, and then kind of projecting forward into 400 gig, and you overlap those with GA dates for, I'll just say optical modules at 100 gig, 200 gig, 400 gig, and 800 gig, you can see that we tend to move pretty slowly. We're not at the bleeding edge, deploying things right when they are available. And once we deploy an ecosystem, we sit in that ecosystem for a good several years before we start ramping that down and ramping up a new technology. And just looking at the turnover and churn in our networks, we skipped entirely any type of 200 gig solution. We're just starting to look at rolling out and deploying our first 400 gig ports in the early part of 2021, the first half, but won't be really deploying 400 gig in earnest until 2022. And we expect that to take some time to reach full maturity in our own internal data center ecosystems, So by the time an 800 gig solution is ready, as others have called it out, we won't be ready at Microsoft. So it's just, again, helpful historical context to kind of frame how real is the need for 800G, at least for us, and especially in light of the power challenges we mentioned before. So I want to revisit Radha's slide here, who I guess he stole from Facebook, but then added this table down here. And I would say just that he's spot on with the radix argument, but I would argue he didn't quite take it far enough. When we project out to 51.2T switches, if you look at the radix there and consider that the lane speed of those is natively 100 gig, that gives you, 512 radix on that switch. And that allows you to build a network that services over 100,000 servers in a data center by leveraging the 100 gig building blocks. So 100 gig being the native electrical lane speed is really the simplest network that you can build. It's one MAC equals one electrical lane equals one optical lane, and the idea here being that you fan out these 100 gig interfaces horizontally, so that you're able to build a highly power efficient and very flat network, kind of as Radha was getting at. And 100,000 servers is nothing to shake a stick at. That's effectively a 100 megawatt data center. That's just massive capacity. So I want to show here just how that looks, at least for this first tier of the network, where again, today, this is revisiting what we do with the DAC cables going to the tier 1 devices using AOCs with a TOR in between. What we envision doing when we're enabled by these advances in photonics, including CPO and the 400 gig availability for the servers, we would have here at the server 400 gig DR4 interface, and that would fan out across these tier 1 switches, providing that horizontal scaling that I was referring to, and in that way allow you to completely eliminate the TOR at the top of rack and just have some type of patch panel or shuffle panel as a demarc at the top of rack now. And when you go and compare the efficiencies of the old way of doing things on the left with this we're calling TOR bypass with the 100 gig lanes, you can see there's a host of advantages. One being the failure domain. A TOR is a single point of failure for an entire rack. And again, if you're serving content, maybe that's not a big deal, but if you're providing compute as a service, and that can be huge, right? Whereas if you're multi-homing your NIC, you have that 4-way resiliency, or I would say in-way resiliency, depending on a number of interfaces or planes on your server. Looking at the switch ASIC count, 4 to 8x in this case, when compared to the number of switch ASICs it would take to build this network here. Space and power, again, reduced space, obviously saving the space of the TOR, and then a third the power, primarily by reducing the number of switch ASICs, but also running more efficient co-package optics on the tier 1 devices. In terms of switch radix, on these, especially when you get to these high radix switches that are coming up in the future, you can't leverage the high radix switches fully. You leave stranded ports on your TORs here because, again, we're just a few tens of servers per rack, but some of these switch chips are 64 or 128 radix. Whereas here, by fanning out again and leveraging the full 100 gig lanes on these switches, you can leverage the full radix of all the switches in the tier 1s on the switch chips. Again, I mentioned before that we typically run some oversubscription going from the TOR to the tier 1. whereas in this scenario, it's fully non-blocking or I guess non-oversubscribed. And then lastly, reach limitations of DAC cables and AOCs are looming, whereas common optical solution like a DR4 based interface would allow you up to 200 kilometers or more of reach. So that goes away. So apologies if I went a little bit over in time, but it's a bit of a nuanced discussion, so I wanted to try and be sure I covered it well. But the power, in summary, the power is the main limiter for beyond 400 gig data centers as we see it. We can't continue to simply scale the link bandwidths while building the networks exactly as we do today. And additionally, the historical ecosystem life cycles would indicate that we won't be ready for 800 gig when the industry is. And really a 32 by 100 gig CPO will suit our needs better. 100 gig electrical lanes will be a foundational building block for power efficient data center designs for the foreseeable future. Just that idea of what I was showing with the Tor bypass. And lastly, future data center networks are going to require a combination of photonic innovation, which we lump CPO into that, optimized network architectures, and advanced hardware implementations. And I think that's it. So thanks for your time.
All right. Thank you, Mark. We really appreciate that, especially that your going green imperative. I think many people across the industry are really working hard on that problem. So I also wanted to say that these slides will be available to everyone. We'll send them out in an email to all the registered attendees, probably within a couple of days. At this point, we're going to take questions for about 15 minutes. We have a lot of great questions that have come in, and we'll try to answer as many of them as we can get to. If we don't, we'll follow up on that as well. So first, Radha, the question of power in DSPs. That's the first one. We're hearing some considerations for PAM5 or PAM6. Are there inefficiencies expected in DSPs when PAM signaling goes up to PAM8 or 16?
So this is a two-part answer. I'll get Ilya to chime in as well. So when you go to a higher complexity in modulation format, you're working against two things. One is your SNR is going up exponentially, the good old Shannon. And secondly, your linearity requirements are going up just as bad. So yes, if you go to a higher order modulation format, let's call it for what it is, you suffer SNR, the game you're trying to beat, and you consume a lot more power in the TIA and driver trying to linearize them. And that's partially one of the reasons why we think PAM4 is a good compromise. Ilya?
Yeah, I think you summarized it really nicely. So just to make it more quantitative, when you go to a PAM6 versus a PAM4, the eye opening for your PAM6 is decreased by a factor of 5/3. So that's already a penalty in SNR of like about 4 dB or so. Also, higher order modulation is more sensitive to many impairments. Like for example, RIN. I mentioned earlier, RIN is a very important impairment in lasers, and it impacts higher order modulation more because it's a level dependent noise. So PAM6 suffers more from RIN, and you actually saw that in my plots where PAM6 kind of exhibited an error floor at higher analog bandwidths. And other impairments, ISI, it's more sensitive to ISI. So there are a lot of advantages. If you can get high enough analog bandwidth for PAM4, it's definitely, there's a big advantage there for robustness, for implementation purposes, it's lower complexity, many advantages, and also backward compatibility, of course.
All right, great. Another question for Radha on the symbol transmit rate. Is it still capped around 25 gigabaud owing to limitations on direct modulation of lasers?
Okay, this is an interesting question. For DMLs, it is probably capped at about 25 gigabaud, although there are announcements from several vendors of DMLs operating at the 53 gigabaud data rate, but largely at 53 gigabaud or 100 gig per lane, DR4, FR4 implementations have mostly been EMLs and silicon photonics. Yes, there seems to be a natural stop at DMLs. I wouldn't count them out, but there seems to be.
Okay, Ilya, what kind of specs are required for the ADC to enable the DSP for the PAM4 receiver?
Yeah, I mean that's a great question. So the ADC is a key component of the system. I went over the requirements on analog bandwidth, and I think those are valid for the ADC. So you need analog bandwidth of better than 45 gigahertz for PAM4, ideally better than 50 gigahertz. And of course, there are many other specs like specs on ENOB, various distortions. And it really probably would require a separate presentation and discussion just on that. But I think the key spec, analog bandwidth, I would say around 50 gigahertz.
Okay. Could you also talk a little bit about the latency? The latency of 300 nanoseconds, is it too large for 800G in a 2K application? And I guess latency of the FEC in general here.
Yeah, that's another very good question. It has a lot of implications and trade-offs. So, when designing FECs, there's kind of a fundamental trade-off between coding gain, FEC overhead, and FEC latency. It's very difficult to have a very large coding gain, very low overhead, and very low latency. You have to make some trade-offs. So we believe, to get the kind of coding gain we need, we try to play as much. We try to optimize that parameter space as much as we can. The overhead, keeping that overhead at around 6%, not more than 6%, and keeping that latency less than 300 nanoseconds. 300 nanoseconds, I think, is a reasonable number. If you think about a 2-kilometer link, the latency, just the propagation delay of that link is microseconds. So I think that latency is still much less than the propagation delay. But it really depends a lot on the application. So if we're talking about it like an AI application where the links are very short, maybe in the AI cluster, then you might need even lower latency. And there are ways to design these FECs that I talked about, the concatenated FECs, to have even lower latency.
So in general, do you think these FECs are going to continue to evolve, and we're going to see them, in the next generation after that?
I think so. Yeah, I mean, I think FEC is a critical technology to enable higher speeds, to enable lower cost optics, and even maybe lower power. I think it's consideration there because I think it's going to evolve. We're going to have a discussion on FEC for sure in the IEEE when we talk about 800 gig. So yeah, it's going to continue to evolve, and it's a very interesting design space. Somewhat different from long haul, where we're just trying to push the FEC to its to the Shannon limit. In data center, there are interesting trade-offs with latency and power. So it's an exciting field actually for FEC designers.
Okay, so a lot of these questions I think have to do with engineering trade-offs, and this next one is looking at PAM6, 90.7 gigabaud, compatible with 75 gigahertz DWDM spacing.
Well, in data center WDM, the channel spacing is actually much wider than the DWDM systems that are used for long haul and metro. So inside data centers, we typically use what's called CWDM, and where the channel spacing is, I think it's around 4 nanometers for CWDM. So it's really not an issue for the spectral bandwidth of PAM6. So I think it's not an issue for the type of channel spacings we use for inside data center.
Okay. Another one for you, Ilya, and that's on MLSD. How many taps are you assuming in your MLSD? And can you comment on the complexity and power?
I don't want to talk too much about the implementation of the MLSD, except to say that we are designing, I would say, innovative MLSD architectures for very low power, low complexity, and it's possible to do that. There are a lot of trade-offs. For example, PAM6 versus PAM4. PAM6 would require more complicated MLSD, so-called trellis architecture. There are a lot of implications. So I probably don't want to get too deep into it, but just to say that the type of MLSDs that we design are low power MLSDs for data center applications.
Okay. Does the additional DFE tap provide improvements because of equalization without noise amplification, or are there other reasons?
Yeah, so to think about the DFE, first consider just the FFE by itself, right? So the FFE by itself can, in principle, invert the channel and completely correct for the bandwidth limitation. But by inverting the channel, the FFE will also enhance noise. And that's where the FFE runs out of juice when you have a very severe bandwidth limitation. The DFE helps by canceling the post-cursor ISI without noise enhancement. So it makes the job of the FFE easier, less noise enhancement, and hence better tolerance to bandwidth limitations. And we saw that in the kind of the simulations that I showed when we added the DFE, both PAM6 and PAM4, but especially PAM4 because of its higher baud rate, benefited a lot from that in terms of its robustness to bandwidth limitations.
Okay, so one more clarification on on that line. Is there any particular reason why you didn't investigate PAM6 with FFE and MLSD? I think you just addressed that. Yeah.
So I touched on that already. So there's several reasons. First of all, PAM6, because of its lower baud rate, doesn't really benefit much from MLSD as you go to, say, as long as the analog bandwidth is, say, greater than 40 or 45 gigahertz, you don't get much benefit for PAM6. But on the other hand, the complexity of the MLSD scales up very rapidly for PAM6. So these are the reasons why it's not really useful, I think, for PAM6.
Okay, a question for Mark. Considering power and thermal performance, would there be some case to adopt CPO at 800G somewhere in your topology, at least to test it out?
Yeah, I guess CPO chiplets based in 800 gig denominations is kind of what's in scope there. Like I mentioned, an 800 gig MAC itself may not be a good fit for what we're looking to do anytime soon. But yeah, as a test vehicle or something, we could see, or like proof of concept and prototyping, we could see, leveraging some of the 800 gig photonic developments in a CPO application, to just get some hands-on time with the technologies.
Okay, and how about Kobo in general? Could you be testing that as an opportunity of reducing power and cost?
Yeah, I was just typing a response to that one. Yeah, so Kobo, as of now, there are some, tinted programs inside Microsoft that are evaluating Kobo in some of those applications. But for our mainstream networking deployments, there is not currently a plan to roll out Kobo. We will be focused on transitioning to co-package optics in the 2023-2024 timeframes. There was also a question on the timelines, so that's answering that one.
Okay, you had another question about how two servers in the same rack can communicate with each other, or in the case of a Tor bypass scheme.
Yeah, they just through the tier 1 switch now, so there's not a Tor anymore, but the chip at the tier 1 would be able to talk to all the servers in the same same row.
In the same rack. Okay. Let's see. I guess there's a still kind of a wider question here that I'm going to give back to Radha and Ilya, and that's kind of to see if you guys together or individually want to give an answer to Mark, to basically address those power concerns.
Okay, as Mark said, power is the elephant in the room. There is no denying. As you go to higher and higher baud rates, is simply we are consuming more power. And Mark has very elegantly pointed out why co-packaging, essentially reducing the SerDes reach between the switch and the package would reduce it. And in his case, he's also advocating for a lower data rate. On our side, we have a multi-prong approach. I'll let Ilya comment as well. And Ilya had said a number of times, a low power FEC, low power MLSD. So the first approach is just architecture. There are several architecture, unfortunately, a lot of which are proprietary, that leads to a lower optimal power consumption. Secondly, this never-ending march, hopefully it never ends, on smaller CMOS nodes. Our current generation CMOS ASICs are 7 nanometer, going to 5. And going to 5, it's not so much on density. The chip, the DSP areas don't scale so much, but the power goes down. I have to go back and take a look how much the power reductions we're getting between 7 and 5, but we are designing chips at the 5 nanometer node. That is one, and these will be the two approaches that we are taking to get power reduction down. And then Mark focused on power dissipation, which is a flip side of power consumption. If we didn't consume so much, you don't have to dissipate or cool as much. But Ilya?
Yes, I agree with you, Radha. So for us, like in the DSP and architecture team at Inphi, low power is really kind of a passion for us. So with every generation of technology, some of the key innovations that we work on are lowering the power of the DSP architecture and the FEC. I think that is actually one of the big differences between, say, long haul and data center is in data center DSP, we really focus a lot on low power architectures. And there's a lot that was done, that we've done, but we cannot publish because it's proprietary implementations. I mean, there are things, you can read about in the literature, various approaches for low power architectures that you can think about. Now, the other thing is, with each generation, we can also reduce power by going to smaller node, right? CMOS node. That also helps, especially for DSP heavy architectures, right? They scale well to lower power as we go to a smaller node. So that should help as well.
Okay. All right. Well, fantastic. And with that, we're just about out of time here. So we're not going to be able to take any more of these great questions that have come in, but we will do our best to answer them offline.